Hello, everyone, and welcome to the worksheet 12 video key. Okay, so we are going to be showing the mechanism of homolytic bond cleavage and then draw the resulting products. So it's showing you the indicated bond, and to draw the mechanism, you just need to use our fishhook arrows to form the two radicals if we were homolytically cleaving that bond. So in all of these cases, we're going to form a hydrogen radical. But the carbon radical will be different in each case. And so we'll also show the carbon radical. So again, same mechanism in all cases. Just make sure that you're drawing your fishhook arrow. And then we draw the resulting carbon radical. So this is a methyl radical, a primary radical. Followed by a secondary radical, a tertiary radical. Now we're going to draw a vinylic radical. The primary radical is really the same as this one, right? So I'll just go over here. Same. Just in case you didn't notice that, there's only going to be 6 different ones. And then lastly, we have the allylic radical. All right, and then it says based on the bond dissociation energy, which is the energy needed to break the bond, rank the above 6 radicals in order of increasing stability, with the most stable or lowest potential energy radical as number 6. So if we are going to be starting with the least stable as number 1, right, we want to look for the one with the highest bond dissociation energy, because they're inversely related. Right, so we would have 464 is the highest value here, so this will be number 1, followed by 439, 423, 414, 406, and then 364. It says comment on the similarities observed between carbon radical stability and carbocation stability. And you explain the observed trends, right? So in general, I would say carbon radical stability parallels. Carbocation stability, because both species are electron deficient. Right, and then we would say, what should we say next? Increased substitution. So for example, primary, secondary, and tertiary. Increases stability. due to hyperconjugation. In both cases. So radicals or carbocations that are vinylic or on an sp2 hybridized carbon are particularly unstable because sp2 hybridized orbitals are more electronegative. Therefore, they don't want to stabilize electron deficient atoms very well. And then I would say lastly, allylic radicals or carbocations exhibit resonance stability. All right. Moving on to the next question. Which CH bond requires the most energy to break? What does that imply about the stability of the carbon radical? So the one that requires the most energy to break, or has the highest bond association energy, would be the vinylic CH bond. And so that what is implied is that the carbon radical that results is the least stable / highest energy. I'm referring to potential energy. So remember that a bond breaking is an endothermic process. So it's going to have activation energy. And if it's going to require the most activation energy, it's going to form the least stable radical intermediate. And then which carbon-hydrogen bond required the least energy to break from our previous data set? So we had, that was the allylic one. Right, and that implies that the allylic radical is the most stable radical, i.e. lowest energy. Okay. Show the initiation wants to focus on. There we go. show the initiation, propagation, and termination steps of the halogenation of ethane. Okay, so ethane, right, is just going to be CH2, CH3, CH3. Make sure you know what ethane is. And if it just says halogenation, I guess it's looking for just a generic mechanism where we can just use X for the halogen, right? And typically there's some light that will be used to do the initiation step. And then the product will be monohalogenated alkane and HX. So the initiation step is going to be the formation of the radicals. So we can just kind of draw XX. If it's a halogen, there'll also be 3 lone pairs, each one. We're just going to do our radical formation. And then the propagation steps will involve first hydrogen abstraction followed by halogen abstraction. So we are going to show ethane. We want to show one of the hydrogens, at least one of the hydrogens drawn out, or we could draw them all out, like a Lewis structure. Either way. Again, we're going to show halogen abstraction. Don't forget to use those 3 different fishhook arrows. And then we'll form HX byproduct and the carbon radical. Note that on ethane, even though there's 6 hydrogens, they're all equivalent. We get the same radical no matter what. Then we'll take this radical and do halogen abstraction next. So we're going to draw X, X. And the radical. And that will generate the product. And regenerate some more of the halogen radical. Right? So this is the starting material, the organic starting material, the organic product. And then we also consume some X2 and are getting HX as a byproduct. So termination steps are technically not, they don't explain the product. The majority of the product comes from the second propagation step, right? So, but there are various termination steps that could happen. So you could have the reverse of the coupling to reform X2. It's just when any two radicals in solution come together. It's also possible for the carbon radical to find a halogen radical and recombine. And then the third possibility would be two of the carbon radicals coming together. To form, in this case, we get some butane. Okay, moving on. Show the mechanism for the following transformation. So first we need to show the initiation step. And then to show how the organic reactant is converted to the organic product, we need the two propagation steps. The first one is hydrogen abstraction. And recall that the bromination is very selective for the most substituted hydrogen. So we'll do hydrogen abstraction. And then the carbon radical does halogen abstraction. Make sure, typically it's not needed to draw any termination steps to explain how this product and this product are formed. So we're just going to do the second propagation step, which is halogen abstraction. And then we reform some bromine radical, which can react with another alkane and complete the chain cycle. Next, we're asked to indicate the most substituted CH bond in each of the following, I should say, molecules. In radical halogenation reactions, it is the most substituted CH bond that produces the most stable radical, and hence where the halogen is incorporated into the molecule. Are there any exceptions to this shown below? So the most substituted bond would be CH bond would be one of the two secondary, right, is more substituted than primary. There's a tertiary position here, which would be the most substituted. All of these are considered equivalent. All 10 hydrogens. I'm just drawing one of them. Here we don't actually have any tertiary positions, so the best we can do is the secondary position. There's actually two of them here. You could draw both of them in like I did here, or just one. There's a tertiary position here, so we'll draw that in. Over here, tertiary position is down here. Now this is the tricky one, right? Because we have the hydrogen here, which would be tertiary, or the hydrogen here, which is allylic, right? So this would produce a tertiary radical, and if we remove the hydrogen here, it would produce a benzoic radical, right? So this one actually has a lower bond dissociation energy. So the bond dissociation energy to produce a benzoic radical is lower than to form a tertiary radical. So this is the one that is the exception, because this is only secondary versus tertiary, but this is secondary and benzoic. Predict the major product of the following radical halogenations. So recall that even though chlorination isn't as selective as bromination, it is still slightly selective for the more substituted halogen, the more substituted position. So we will go ahead and draw that in. Will still be the major product. Here we have only primary and secondary positions. So we'll just put it at one of the two secondary positions. And note that this is a racemic mixture. Make a little note. And I'm assuming, even though I didn't write it, I'm trying to get you to do monohalogenation. Okay, so here, the allylic position would be the most reactive. By the way, typically NBS might be used instead of bromine here, because bromine again can react with the alkene. But even if it's bromine, you can still clearly wanting us to do a radical halogenation and not any other reaction. So we can go ahead and do that reaction. So again, the bromine will end up here, but remember that with radical intermediates that are resonance stabilized, there'll be two products. Okay. For here, we should put the bromine at the benzoic position. So technically, this is a racemic mixture. This would be a racemic mixture. And so this. And then next we have bromine. The most substituted position is here, but recall that it will get rid of the stereochemical information at this carbon. So we'll actually end up with a racemic mixture here, but this one should not be touched. So we'll end up with a mixture of diastereomers. And this one's a bit tricky. Where will the chlorine go, right? There's a bunch of different allylic positions. However, this center one would be allylic to both double bonds, and therefore the radical would be doubly resonance stabilized. So it would be more stable radical and therefore a lower energy pathway. So we'll put the chlorine here. And then initially you might think that, look, that should be a chiral center, but this group is identical to that, so it isn't. Fill in the empty boxes with the proper structures or reagents. So we have the bromine will go in the most substituted position. Ask yourself, is that a chiral center? Bromine, right? It's going to go in the most substituted position. So we just need to draw the starting material without that present. And then here we have the addition of chlorine. So we should write CO2 and either light or heat. And again, chlorine, even though it's not as selective, it should still mostly go in the most substituted position. And lastly, we have kind of a tricky one to get you guys' brains juices flowing. So it says, for the reaction below, draw the structure for every possible monobromination product, including stereoisomers. All right, so if we're technically drawing every single one, then I guess we should include also the vinylic positions, even though those are very, very unlikely structures. We can, technically it says every single one in bolded letters, so we can go ahead and include those as well. So we would put the bromine here, and that would be different than if it were going down here, and that's because this would be considered a cis alkene and this is a trans alkene. As we know, those are different, right? And we could also technically have the bromine here. Right? And later on, we'll put like which ones are kind of very unlikely to form, but technically, as I said, every single one. And what else could we do? What if we put the bromine in one of these two methyl positions? So if I was to put the bromine on one of these two methyl positions, and we'll put it here, right? Did I form any stereocenters? Actually, I might want to make a little note of this. And the answer is, let's look at this carbon, right? This now has 4 different groups attached. So technically, we need to draw either draw one on a wedge and one on a dash and then switch it, right? So, or at least put, right, racemic mixture. Maybe I'll even include what that looks like in just in case people did it the other way. So if we were drawing a racemic mixture, we just need to put one group on a wedge, one group on a dash. It could be one of the other groups, it doesn't matter. This is equivalent to that drawn out. Okay, what else could we possibly have done? What about if the bromine goes here? This will also create a racemic mixture, which again you can indicate one of two ways. You can either just draw it on using a regular bond and then put racemic mixture, or draw it out. One way to do that. Okay, where else could that bromine go? What if that bromine goes here? That does not generate a chiral center. So we'll go ahead and draw it out. Okay, so that, and then lastly, if you were to place it at one of these two terminal methyl groups, technically that would create a chiral center here. Now it would have 4 different groups attached. Let's draw that last possibility. Draw that out. Okay, so how many different compounds, monohalogenated, monobrominated products can we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But certain ones are technically very unlikely. Like these would be very, very unlikely to form, right? Also, the bromination at the primary position would be very unlikely to form. And this is another primary position. This would be secondary, but this is definitely going to be the major product because it's bromination at the only tertiary carbon. And there was no ability to make an allylic position because the allylic position is blocked with the 2 methyl groups. Okay.